Hi, welcome to this lecture on elementary sorting algorithms. Here's the outline for this lecture. We'll first talk about the rules that we will follow in implementing various sorting algorithms, and then we will discuss some elementary sorting algorithms such as selection sort, insertion sort, and Shellsort. And then we'll talk about how you visualize sorting algorithms and compare them qualitatively. And finally, we'll discuss how you compare two sorting algorithms in a quantitative manner. Okay. So let's first start with some rules of the game. First of all, what is this problem of sorting? Well, it's the process of rearranging a given sequence of objects so as to put them in some logical order. So you're given a collection of objects and you're asked to put it in some order. So that's the problem of sorting. So for example, your credit card bill typically presents transactions ordered by date. So the transactions there are sorted by date. Okay. Now, in our implementations of the various sorting algorithms, what we're going to do is follow a conservative practice, which is to include the statement, the assertion statement, assert is sorted of A in all our test clients, right? To certify or to make sure that the array entries in this array A are indeed sorted, okay? Once the sorting algorithm is finished. So if A has been correctly sorted, then this assertion is going to be a no op. Otherwise, there will be an assertion error. And once we see an assertion error, we would know that our sorting algorithm is flawed and that we need to fix it. Okay, so we're going to do this in every test client. We will have this assertion statement just to make sure that our implementation of the sorting algorithm is correct and it properly sorts the given array A. Now, how do we compare two sorting algorithms? Well, we're going to compare the performance of two sorting algorithms by simply counting the number of basic operations, which are going to be comparisons and exchanges or array accesses. Okay, so those are the operations that we're going to keep track of in comparing two sorting algorithms. Now, there are two types of sorting algorithms. Ones that sort in place and use no extra memory. Okay. And these are called in-place sorting algorithms. And then you have algorithms that need enough extra memory to hold another copy of the array to be sorted. Okay. And we're going to look several examples of in-place sorting algorithm, and we will look at one example of an algorithm where you need an additional array, which is typically called the auxiliary array. And the auxiliary array has exactly the same size as the input array. Okay, so we'll look at these two types of sorting algorithms. Our code for the different sorting algorithms is going to be effective for any item type that is comparable. Okay, so what that means is we're going to write fairly general sorting algorithms that are going to be able to sort a collection of any comparable type. So let's take a look at a template program, and our implementation of every sorting algorithm is going to have this structure, right? So for each algorithm, we're going to have a program that has the name of the sorting algorithm for its name, okay? And then it's going to have all these methods inside of it. So let's go through these methods carefully. So the first two methods are the only public methods that you will see in each implementation. Okay. Now, the first method is public, static, and it's void, meaning it doesn't return anything. It's called sort, and what it does is it takes an array of comparable objects. Takes an array A of comparable objects and simply sorts it. Okay? It doesn't return anything, but it has a side effect of sorting this array A. So this particular version of sort works on an array of comparable objects. Okay, and then the details here, meaning the implementation of the sort method, will vary for different sorting algorithms. right? So we're going to see various algorithms such as insertion, selection, and so on, and the implementation will vary depending on the sorting algorithm that we are considering, right? So it's different for different algorithms. Okay. So that's one of the two public methods, and the other method is an overloaded sort method. Okay, so here the first argument is an array A, not of comparable objects but just objects. So you can sort a collection of objects using this method, but in that case you need to tell the sorting algorithm how two items from this array ought to be compared, and the way you do that is by specifying a second argument C, which is an object of type comparator. Okay, so we have two sort methods, one that operates on an array of comparables and the second that operates on an array of objects, but in that case it also requires a comparator object as an argument. Okay, because it's this comparator object that will tell the sorting algorithm how to go about comparing two objects from this array. Okay, so here again this implementation is going to be different for different algorithms. Okay, and now we already have some experience with methods having this signature. We have seen arrays dot sort with one argument, namely an array of comparable objects, and we've also seen arrays dot sort with two arguments, the first argument being an array of objects and the second one being a comparator object. Okay? And we used these methods, for example, to sort an array of planet objects which were comparable, and then we also and when we did that, the sorting happened and the sorting was done based on the names of the planet. Okay, so planet objects were comparable by their names. And then what we did was we also called arrays.sort on the array of planet objects, but we gave it a comparator, and this was the moon comparator. Okay? And when we did that, sort had the effect of sorting the array of planet objects by the number of moons. Okay, so we already have experience with these sort methods. Okay, arrays basically implements these two versions of sort following a similar sort of template. Okay, it has one sort method that sorts an array of comparable objects, and it has another sort method that compares an array of objects given a comparator object. Okay, so those are the two public methods, and then we have a whole bunch of private methods which are simply helpers for the sorting algorithms. So let's go through these. So the first private method is called less, and that's what the sort algorithm is going to use when it needs to compare two comparable objects V and W. Right? So if the sorting algorithm needs to check if V is less than W, it would make a call to less, giving it the two comparable objects as argument. And since V and W are comparable, the implementation makes sense. It simply returns the value of V dot compared to with W less than 0. So V and W are comparable, so we can make a call to the compare to method from the comparable interface on V, giving it W as an argument. So if this guy comes back with a negative number, we know that V is smaller than W. If it comes with a 0 or a positive number, we know that V is either equal to W or greater than W, because that's the convention that we follow in implementing compare to. Right? So less is a private helper that lets you compare two comparable objects V and W. What about this overloaded less method? Well, here the less method compares two objects V and W, not necessarily comparable, they're just objects, but in that case we need a comparator that we can use to compare these guys. Okay, so that's the first argument. So the first sort method will make use of this less, and the second sort method will make use of this guy here. Okay, by providing it a comparator object, which is basically this, right? And how do we implement this method? Well, C is a comparator object, so we can say C.compare. So compare, if you remember, is a method in the comparator interface. So we call C.compare, giving it the two objects V and W as argument, and compare the return value with 0. So if it is less than 0, it would mean that V is less than W. Otherwise, V is greater than or equal to W. Okay, so that's what we return. Okay, now what if you want to exchange two objects in an array, and these objects have indices I and j, meaning you want to swap the values at I and j in this array A? Well, here's this is the helper that will do that. And the implementation is the standard idiom for swapping two values. So you store the value at I in the array in some temporary variable, and then you say A at I is A at j, okay? And then you say A at j is what the value of A at I was to begin with. Okay, it's the value of that temporary. Okay, so that's a private helper that exchanges the values at index I and j in the array A. IsSorted is a method that we can use to check if this array A of comparables is sorted or not. And the way that method works is it simply makes a call to isSorted, which is this guy here. Okay. Giving it A for the first argument, 0 for low, and A.length minus 1 for high. So this particular method is capable of checking if this array is sorted from the elements low to high. So it can check if a segment of this array from low to high is sorted or not. And then this guy simply calls this method, giving it a segment which is the entire array. So 0 for low and A.length minus 1 for high. So let's see how this method is implemented. We start I at low plus 1, and I goes all the way up to high in increments of 1, and then we check if A at I is less than A at I minus 1. So if this condition is true, then you're looking at a value. So you have a whole bunch of values. So the height represents the magnitude. Okay, so we have all these guys sorted, and then let's say you have this particular element here that you're looking at. So this is like A at I, and it is smaller than A at I minus 1. Okay, so this array we conclude is not sorted, mean return false. Right? So if you find an element I that is smaller than the previous one, you say that the array is not sorted. Otherwise, once the loop is exhausted, you return true, saying that the array A is sorted from low to high. Right? The next method is sorted, again overloaded, but this time its input array is an array of objects, and it's given a comparator, right? So how does this work? The same idea, this guy makes a call to this version of isSorted, giving it A for the first argument, comparator as the second argument, 0 for low, and A.length minus 1 for high. So this particular method is capable of testing if this array A of objects, given a comparator C, is sorted from low to high. It can check if a particular segment in the array is sorted. Okay, how does it do that? The same idea as before. So I starts at low plus 1, goes all the way up to high, but now notice that when we want to check if this guy is less than this guy, what's the version of less that we call? We call the version that takes a comparator as the first argument. Okay, okay, so if A at I is less than A at I minus 1, then we know that the array is not sorted, because you found an element. So you have a whole bunch of sorted things, and then you find some A at I which is smaller than the previous one. So this array is not sorted, right? So we return false. Otherwise, at the end, we return true, meaning the array is sorted. And then we have this helper called show that simply takes an array of comparable objects, A, and prints them out. So I starts at 0 and goes all the way up to the length of A in increments of 1, and we simply print out A at I along with the space after. right? And then at the end we print a new line character. Okay, so those are all the helpers, and then we have a little test client. And what that does is it reads a whole bunch of strings from standard in as an array A of string objects, and then we simply call the sort method, all right? And that sort method is an implementation of some sorting algorithm, and we're going to look at several examples later on. So sort takes that array A as an argument, sorts it, and then what we do is we assert on A being sorted. So we call this isSorted method on A and assert that it is true. So if A is indeed sorted, then this is going to be a no-op, and then we end up printing the sorted array A, which is a call to this helper method show. Okay? But if for whatever reason sort didn't do its job, then this assertion is going to fail, right? And then we know that there is something wrong with our sorting algorithm. We go about fixing it. Okay? So that's the template that we will follow when we implement our sorting algorithms. And here is some input and output. So if we run sort algorithm, this program that I just walked you through, giving it these strings as standard input. So S is a string, O is a string, R is a string, and so on. And then and if I hit the enter file character, the program comes back with the sorted output. Okay, so it sorts this input and prints out the elements in sorted order. Okay. All right, so that's the template that we're going to follow. And going forward, when we discuss each of the sorting algorithms, I am only going to focus on one method, okay, which is the public static void sort method that takes an array of comparables. Okay. So for each sorting algorithm that we will discuss, I will just show you the implementation of this method for that algorithm. Okay. Because that's the only method that's going to be different for each sorting algorithm. Other than that, you're going to have the same set of helpers and so on that we have discussed in this template. Okay. All right. So with that, we are ready to talk about our first sorting algorithm, which is selection sort. So selection sort works as follows. What we do is we first find the smallest item in the array and exchange it with the first entry. Once we do that, the first entry is the smallest item in the array. And then what we do is, starting from the second item, we scan through the array and find the next smallest item and exchange that with the second entry. So once we do that, the first and the second values in the array are the first two smallest items in the array, and then we repeat the process. We start at the third item, we scan through the array to find the next smallest and exchange that with the third entry, and so on and so on and so on. Okay? So that's basically the gist of selection sort. And here is how it is implemented. So this program is called selection, and if you look at this program, it will have exactly the same sort of structure that I just walked you through. Okay. The only thing that will be different is the implementation of this method sort, which is what implements the particular sorting algorithm that we are discussing, which in this case is selection sort. Okay, so let's go through this method. So the method is sort. It's given an array of comparables, A. We first get the size of A as capital N, and then I starts at 0 and goes all the way up to capital N in increments of 1. Okay? And then we say that the index of the smallest element, min, is I, the current value of I. Okay? So when I is 0, min is simply 0. And then in this loop, what we do is we start j at I plus 1 and go through the entire array. Okay? And we check if A at j is less than A at min. So if you find an element that is smaller than the current minimum, we make that element be the new minimum. So if A at j is smaller than A at min, the new value for min the index of the smallest is j. Okay, and you keep going. And once we do this, once the inner loop is done, we have managed to find the smallest element in the array starting at index I plus 1. Okay, and then outside of this inner loop, what we do is we simply exchange the values at indices I and min in the array A. Okay, so the smallest element takes the place of index I, right? So when I is 0, the smallest element in the array is placed at index 0. Okay, when I is 1, the the next smallest item is placed at index 1, and so on and so on. Okay, and notice the calls to the private helpers that we talked about before. So less is a helper that we call here, and then exchange is a helper that we call here, right? So that's selection sort. Let's look at a trace of this algorithm. Okay? And this trace is right before the call to that exchange method. So let's go through this. So our inputs are these S, O, R, T, and so on, and these are stored in the array A. So n here is a dot length, which is 11, right? So what are we looking at here? We're looking at the values for the two variables I and min, and these values are right before the call to exchange. Okay, so in the first iteration of I, what does the inner loop, the j loop, do? Well, it starts at I plus 1, which is 1, and simply scans the array and finds the smallest element. So which one is the smallest element? It's A, whose index is 6, right? That's why min is 6. And then what exchange will do is it will exchange the values in the array A at indices I and min. Okay? That's how this I comes here and this S goes here. And once that is done, we have the smallest element in the array at index I. And then I is incremented to 1, and j starts at I plus 1, which is 2, and it goes about finding the smallest element, which is E now, because if you start here and scan the array, what is the smallest element? It is E, whose index is 4. That's why min is 4. And exchange will simply exchange these values. So O is going to go there, and E is going to come there. So that's why you see E here and all that. Okay, and then I now becomes 2, and j starts at I plus 1, which is 3, and tries to find the smallest element. Okay, so we scan the array starting from here, and we find the smallest element as E, whose index is 10, and hence the value here of min is 10. And what does exchange do? It brings this I here, and this R takes the place of E, which is here. Okay, and then I is incremented to 3, and j starts at 4 and tries to find the smallest element, which is M, whose index is 7, and we simply exchange these guys. So O goes there and M comes there. That's what you see here. Oh, and so on and so on and so on. And once the I loop is completely done, what we have is the entire array A completely sorted. Okay, so that's how selection sort works. Now, what's the running time of selection sort? So selection sort uses approximately n squared comparisons and n exchanges. All right, and selection sort is completely agnostic about the input data, and what that means is it takes just as long to run selection sort for an array that is already in order, or for an array with all the keys equal, as it does for a randomly ordered array. So no matter what the input is, if it is randomly ordered or if it is completely ordered to begin with, or if all the items are the same, selection sort will still take the same time. All right, which is quadratic in the number of comparisons and linear in the number of exchanges. Okay. So selection sort is not sensitive to the input. Even if the input is completely sorted, selection sort is still going to run in quadratic time. Our next sorting algorithm is called insertion sort. And here the idea that we use is similar to the technique that people use to sort bridge hands, right? So you consider the cards one at a time, one card at a time, and you insert each card into its proper place among those that are already considered. Okay, that's how you typically sort a bunch of cards in your hand, and that's the idea that we use to implement insertion sort. And here is the code for that. So this particular implementation is called insertion, and it's going to have exactly the same template as we've seen before. So the only difference is going to be the sort method, which is what implements the insertion sort algorithm. We are given an array of comparables. We first get the length of the array as n, and then we have two loops. I starts at 1 and goes all the way up to n, and then the j loop, it starts at I and it goes backwards. Okay, j starts at I, and as long as j is greater than 0, okay, and as long as the element that you're looking at, a at j, is less than the previous one, we keep exchanging the values at j and j minus 1. All right, so you can think of this as such. So let's say you have a bunch of sorted elements, right? And then let's say you have that guy there, right? So how do we put this guy in the right place? Well, at this stage, I is going to point to this fellow here, and I is going to point to this guy here, and j simply starts at I, so j is also going to point to that fellow. And then what we check is j greater than 0? Well, it surely is greater than 0. Is it smaller? Is a at j less than a at j minus 1? Well, this guy is smaller than that, so what we do is we swap these two guys. Okay, so this bigger one is going to come here, the smaller one is going to go there. And then what we do is we compare this guy with this one. Is it smaller? Yes, it is. So we swap those two. So so this guy comes here, and then we compare that with this fellow. It is still smaller, so we swap. Compared with this, still smaller, we swap. And then when we get here, you know, think of this element being now here. We compare that guy with this previous one. Well, now this condition is not true because this element is bigger than the previous one. So when that happens, you know that this element is in the right place, right? And this is basically the idea that you use to sort a bridge hand, right? So so then the j loop is done, meaning you've found the right place for this element, and then you go and do the same thing for the next element, find the right place for that, and so on and so on. Right? So j starts at I, and as long as j is not at the first element, you keep checking if a at j is less than a at j minus 1, and if so, you simply exchange the values at j and j minus 1 in the array A. Okay, so here again we make use of our helper methods that we talked about before, less and exchange. Right? So that's insertion sort. It's a fairly straightforward idea. So let's now look at a trace of insertion sort, and this trace is right after the inner loop is exhausted. Okay, meaning you found the right place for the element at j. So here's our input. So these are the strings that are contained in A. So here again n is 11. I starts at 1 and j starts at I. Okay, so I is 1, j is also 1. What do? We compare the element at j with the element at j minus 1. Well, it is smaller, so this O goes here and this S comes there. And then j becomes 0, but now the inner loop is done, right? And the value of j is 0. And that's basically the final index of the element at j. Okay, so you found the right place for this particular element. That's what we're saying. Let's take the next iteration. So I now becomes 2. J, so I is pointing to this R, and then j starts at I, so j starts at R, and we simply compare it with the previous element. R is smaller than S, so it comes here, S goes there, and now we compare R, which is here, with O, but R is larger than O, so this R is in its right place, given by j equals 1. Okay, so the inner loop is now done. So now O, R, S, they are all sorted. And then I becomes 3, so I is pointing to this T here, and j also starts at that element, and you simply compare A at j with A at j minus 1, but T is larger than S, so the j loop is done right away because T is already in the right place. Okay, so now O, R, S, T are all sorted. I becomes 4, so we are looking at this guy here, E, and j also starts there, and it compares E with T. It's smaller, so E goes here and T comes there, and now you compare E with S. E is smaller, so S goes there and E comes there. You compare E with R. E is smaller, so R comes there and E goes there. You compare E with O. E is still smaller, so O comes there and E goes there. Okay, so that's how E ends up here at j equals 0, and the inner loop is done. So now notice that E, O, R, S, T, the first 4 elements are in the proper place. Okay, and then we continue, so on, so on, so on. And once the outer loop is done, then we have the entire array sorted. Okay, so that's insertion sort. What's the running time of insertion sort? Well, it turns out that insertion sort uses approximately n square comparisons and approximately n square exchanges. So it is also a quadratic time algorithm, just like selection sort. But insertion sort is a much better algorithm than selection sort, right? So it is particularly good for partially sorted arrays, meaning arrays where you have these segments that are already sorted. So that's what we mean by partially sorted arrays. And insertion sort is also an excellent algorithm for sorting tiny arrays. Okay? And insertion sort doesn't suffer from the problem that selection sort has. So for example, if the input is completely sorted, then insertion sort reduces to a linear time algorithm. And you can think about why that is the case. Right? So if the array is already sorted, insertion sort runs in linear time, right? Because the inner loop doesn't do any work in that case, all right? But that was not the case with selection sort at all. So regardless of whether the input array is already in order or not, selection sort is a quadratic time algorithm, whereas insertion sort is sensitive to the input array, right? The next sorting algorithm we're going to discuss is called Shellsort, and it is basically a generalization of insertion sort. Okay? And it does better than insertion sort by allowing exchanges of array entries that are far apart. Okay, so it first makes exchanges of array entries that are far apart to produce partially sorted arrays, which can then be efficiently sorted using insertion sort. I mean, the previous slide we said that insertion sort does really well with partially sorted arrays. So what we do in Shellsort is first, prepare the array, so to speak, such that it is partially sorted. Okay, and we do that by making these exchanges of entries that are far apart. Okay, and then we call insertion sort, which works on a partially sorted array and puts it in total order. Okay, so that's basically the gist of it. So the key idea then is to rearrange the array such that if you take every hth entry starting anywhere yields what is called an h sorted subsequence. Okay, so we look at elements that are h elements apart and then we exchange them, we order them. Okay, and then finally we do an insertion sort on that partially sorted array. So let's look at the code. So this program is called Shell, and it has exactly the same structure as the other sorting algorithms. And here is the sort method, which is given an array of comparables. What we do first is get the length of the array as capital N, and then we initialize this variable h to 1. All right, and here what we are doing is, as long as h is less than a third of n, we say the new value of h is 3 times the current value plus 1. And at some point this loop is going to exit, and when the loop exits we have some value for h. Okay, and what we will do next is simply sort the elements that are h apart. Okay, so let me give you a concrete example. Let's say n was 16. Okay, what is the value of h then for this particular value of n when this loop terminates? Well, let's see. So h starts at 1. So n over 3, if you perform integer division, is what? Is 5. So n over 3 is 5 because n was 16. Is 1 less than 5? It is. So the new value for h, so h starts at 1, now it becomes 3 times h, which is 3 times h plus 1, which is now 4. Okay, now is 4 less than 5? It is. So the next value for h is 3 times 4 plus 1, which is 13. Okay, is 13 less than 5? It's not, so we are done with the while loop. So what we have managed to find is the value for h as 13. So what we will do next in this while loop is take that input array of size 16 and first sort the elements by only looking at elements that are 13 apart. So you might have an element here, you might have an element here, where and they are 13 apart. Okay? And another element here that is 13 apart, and so on. So we basically only look at these guys and put them in order. And then what we do is, in the next iteration, we look at elements that are 4 apart and do the same thing. So the next iteration, you look at elements that are 4 apart. So 4 here, 4 here, 4 here, and so on, and put these guys in order. And then finally, you look at elements that are 1 apart. And when h is 1, you're looking at the standard insertion sort. Right? And when h is 1, the array is already like partially ordered. So insertion sort does really well in putting that array into total order. Okay, so that's how this algorithm works. So let's go through it in some detail now. So we've identified the value for h now, and as long as it is greater than or equal to 1, so for this particular example it was 13, what we do is I starts at 13, and as long as I is less than n, we go in increments of 1, and the inner loop j starts at I. So if I is 13, j starts at 13. And then as long as j is greater than or equal to h, which was 13 to begin with for this example, and as long as a at j is less than a at j minus h, so notice we are comparing elements that are h apart. So 13 apart, for example. So if the element here is smaller than the element here, which was 13 apart from this guy, then we exchange them. Just like what we did with insertion sort, the only difference is that you're looking at elements that are h apart, okay? And then even the decrement is quite interesting. It's not j minus minus, it's j equals j minus h, okay? So you compare this guy with this guy, and so on, and then you compare this guy with this guy, and so on. Okay, so you're comparing elements that are h apart. Okay, so once this outer for loop is done, all the elements that are h apart are sorted. And then what do we do? We cut the value of h by a third. So if h was 13, h integer division 3 is 4. So that's the new value for h. And then we repeat this process. And in that case, this part of the code is going to order the elements that are 4 apart. Okay? And once that is done, h is reduced by 3. So 4 divided by 3 using integer division is 1. And 1 is greater than or equal to 1. And when h is 1, this code here is the standard insertion sort. So standard insertion sort when h equals 1. So you can in your head replace all the values of h by 1, and if you stare at this piece of code, it will look exactly like the insertion sort algorithm that we discussed before. Okay, but the wonderful thing is that in the last step, when we perform insertion sort, the input array A is already partially ordered. Okay, so insertion sort does really very well in putting that array into total order. Okay, so that's how Shellsort works. It's a very elegant algorithm, and it's basically a generalization of insertion sort. So here is a trace of Shellsort after each h sort. Okay, so the input is that, and here n is 16. You have 16 elements to sort, and then so when n is 16, we calculated h, the initial value for h, as 13. So what we do is we simply sort elements that are 13 apart. So you compare s. So you compare this guy with this guy, 13 apart, and p is smaller, so p comes here and s goes there. Okay, and then what we do is we compare the next element with element that is 13 apart, h with l, but h is already smaller than l, so no exchange is needed. And then we compare this e with that e, 13 apart. They're the same, so no change is needed. Okay, so now we are done with 13 sort, and what we have is this as the values in that array. Okay, and now what happens to h? Well, it's cut down by 3, so the new value for h is 4. So we do 4 sort. So we compare this element with an element that is 4 apart. L is smaller, so it comes here and p goes there. Then we compare this guy with this guy, but h is already smaller, so it stays where it is. Then we compare e with o. They are in the right place, so nothing to do. And then we compare L with R, no change needed. We compare P with T, no change needed, and so on and so on and so on. Okay. So at the end of 4 sort, what we have are these values. Okay. and once 4 sort is done, what's the next value for h? Well, we cut down 4 by 3, and what we get is 1. So now we do standard insertion sort. Okay, so I starts here at E, and J also starts there, and we simply compare that element with E. Well, E is smaller, so E goes there and L goes there. Okay, and then I is this value here. J also starts there. It's compared with L. Well, it's smaller, so this E comes here and L goes there. And then we are looking at this particular input, A. A is compared with L. It is smaller, so L is going to go there. And then that A is compared with E. It is smaller, so that E goes there. And then the A is compared with this E. It's smaller, so the A goes there. Okay? So it's basically the standard insertion sort. Right? So once one sort is done, we have the entire array completely ordered, and that's what you see here. Okay, so when n equals 16, we first perform 13 sort, then we perform 4 sort, and then we perform 1 sort, which is the standard insertion sort, and the whole array is completely in order. All right. Okay. Now what's the running time of Shellsort? It turns out that Shellsort uses approximately n to the power 6 over 5 comparisons in the worst case. By worst case, I mean where the input is reverse ordered, meaning it's exactly the opposite of the order that you want. All the elements are in descending order. And when that is the case, Shellsort uses approximately n to the power 6 over 5 comparisons. Right? Now, there is no mathematical result that is available for the number of comparisons in the average case, meaning for randomly ordered input. But we have strong reasons to believe that for the average case, Shellsort is linear rhythmic, or something like that. Linear rhythmic plus, remember, it's n log n. Right? So in the average case, when the input is sort of randomly ordered, we have reasons to believe that Shellsort is roughly linear rhythmic. Okay? But we don't have any concrete results for that. All right? So Shellsort is a very, very efficient algorithm. Okay? Because in the average case, its performance is comparable to linear rhythmic. Right? So it's extremely efficient. Okay. Now, how do we go about comparing sorting algorithms qualitatively? Or well, we can do that visually, and here is a nice website that lets you do that. So if you go to this website, you can visualize how different sorting algorithms work. Right? It's a fantastic website, and what you see here as these column headers are the different sorting algorithms, like insertion, selection, shell, which we saw in this section, and merge, heap, quick 3, and so on, which we will see in future lectures. We are not going to look at bubble, but anyways, on the columns, what you have are sorting algorithms, and here on the rows you have different types of inputs. Okay, inputs that are random. So as you can see here, these inputs are all random. And then you have inputs that are nearly sorted or partially ordered. And then reverse ordered, so in descending order. And a few unique elements. Okay? Meaning lots of duplicates. Right? That's what it means. So different types of inputs, different sorting algorithm. And what you can do is you can click on a particular sorting algorithm. So let's say you click on that and you click on that. So when you do that, you visually see, you see animations showing how these two sorting algorithms work on that particular random input. Okay, and you can sort of like qualitatively get an idea as to which one is better. Okay? Whichever one finishes first is the better algorithm. So you can qualitatively figure that out. Similarly, you can compare the performance of, let's say, selection sort and insertion sort on nearly sorted arrays. And we sort of have a rough idea on what to expect. We expect insertion sort to do much better than selection sort. And you can check that out. Just click these two guys and see which one finishes first. Okay, so this is a fantastic website that I strongly encourage you guys to check out. And this website provides you a qualitative way of comparing two sorting algorithms. Here is another website that's fantastic. That's the URL. And if you go there, you can watch all these YouTube videos. And each video is basically an instructional video via folk dance on how a particular sorting algorithm works. Okay. So for example, you can learn Shellsort via this Hungarian folk dance. All right. Or you can learn selection sort with this gypsy folk dance. So it's a really fantastic website, and these guys have done a phenomenal job explaining topics in computer science through performing arts, right? And this is another website that I strongly encourage you guys to check out. Okay, and and believe me, this is the closest that computer science will ever get to the arts. Okay, the last bit in this section is to get a quantitative idea on the performance of sorting algorithms. Right? So how do we compare two sorting algorithms quantitatively? And this program, Sort Compare, lets you do that. Okay, so let's walk through this program. So it has this method called time that takes two arguments. It takes the name of an algorithm that we want to use, and it also takes an input array. So what it's going to do is it's going to run this particular sorting algorithm to sort that input array, and it's going to simply return the time taken to sort that input using that algorithm. And the way it does that is by using a stopwatch object. So you create a stopwatch object, and depending on which algorithm you passed as an argument, it's going to invoke the corresponding sort method. So if alg is selection sort, then it's going to call selection.sort, the static method sort inside of selection, and it gives it the input array to sort. Okay, so that will go about sorting the array, and then at the end we simply return the elapsed time, meaning the time that it took for selection sort to run on that particular input. But if our input was, let's say, the system sort, in that case, we simply call the sort method from arrays, which is Java's sorting algorithm, giving it the input as an argument. And we return the elapsed time, meaning how long does Java take to sort that input. Okay, so time basically tells you the time that it takes to sort this particular input of double objects using this particular algorithm. What about this method, time random input? Well, here we get the name of the algorithm as an argument, the input size, and the number of trials. All right, and what we do is we initialize a variable called total to 0. We create an array of double objects of size n, and then we perform capital T number of trials. Okay, that's this argument. And for each value of little t, what we do is we initialize this array A to be an array of random doubles. Okay, so A at I is simply a random double. And then what we do is we simply make a call to time, which is this method here that we talked about, giving it the sorting algorithm as an argument and this input, this random input. And whatever the time that is returned, we add to this total. Right? And at the end, we simply return total. So what are we returning here? We are returning the total time that it takes to sort a random input of this size using this algorithm for these many times. Okay. what about this method? Well, it's the same idea, but here the input that we're going to prepare is not a random, but it is completely sorted. Okay? Because at times we want to check how a particular algorithm, sorting algorithm, performs on an already sorted array. Okay? So that's why we have this method here. So here again, we take an algorithm name as an argument, the input size and the number of trials. We initialize total to 0, create an array A of size n. We perform capital T number of trials, and each trial involves setting up this array A with just sorted values. So A at I is simply I. So convince yourself that once this loop is done, A is a sorted array. All right? And then we make a call to time, giving it the algorithm as the first argument and the array A as the second argument. And that time is simply added to total, and at the end we return total. So here, what time sorted input returns is basically how this algorithm performs on an already sorted input of size n, and we perform this experiment t times. Right? And then we have a main method where we receive 4 command line arguments and an optional 5th argument. The first 2 command line arguments are the names of 2 sorting algorithms that we want to compare. Okay? And then the third and the 4th command line arguments are the input size and the number of trials we want to perform. Then we initialize 2 variables, time 1 and time 2. Time 1 is going to store the time that it takes for algorithm 1. Time 2 is the time that it takes for algorithm 2. And then if there is a 5th argument, and if it is the string sorted, then we compare the 2 algorithms on sorted input. Okay? So we make calls to this guy here. But if we don't specify a 5th argument, then we compare the 2 sorting algorithms on random input. So we call time random input from the previous slide. Okay. All right. So once we are here, we have the time that it takes to sort an input of size n using the 2 algorithms, ALG1 and ALG2. And what we do is we simply report the result. So we say that for n random doubles, algorithm 1 is so many times faster than algorithm 2. Right? This is simply a ratio of the time taken by the 2 algorithms to sort an input of size n. So let's look at some input and output. So we run sort compare, this program, giving it Shellsort and Selection Sort as the first 2 inputs. So we want to compare Shellsort and Selection Sort. And we say n is 10,000. And then we say capital T is 100. And the program comes back with this output. It says that for 10,000 random doubles, Shellsort is 51 times faster than Selection Sort. Okay? And that does make sense because Selection Sort is quadratic, and Shellsort, though we don't have a mathematical formula for it, we have reasons to believe that it is approximately n log n, and this guy is much better than n squared. Again, that's what we see. So Shellsort for sorting 10,000 random doubles, it does about 50 times better than Selection Sort. So from this, we can quantitatively say that Shellsort is significantly better than Selection Sort. Right? Okay, so that concludes this lecture on the basic or elementary sorting algorithms, namely Selection Sort, Insertion Sort, and Shellsort. Okay, and in future lectures we are going to look at other sorting algorithms, but we will follow the same structure. We'll stick to that template that we discussed in this lecture. Okay, all right, so thanks for your time.